Hey, welcome back. So next up is partial fraction decomposition. So we're going to use this to break down a single fraction, single rational function, into the numerous fractions that create it. So the idea is what we're going to do is we're going to be factoring a denominator of that rational function, setting up new fractions based on that denominator, and then using a variable a and b in the numerator to solve the resulting system that you create with that scenario. Now, solving this system, you're welcome to use the two new methods we talked about with matrices, Cramer's rule, or with the inverse matrix. Both would be very useful if you're writing computer programming code to solve these things. However, since we're going to be dealing with 2x2 systems, you're probably better off with elimination or substitution. They're a bit easier to work out by hand without the aid of a calculator or a computer. And that's what the method I will use when solving these. So the idea here is, so we have negative 3x minus 33 over x squared plus 4x minus 5. We're going to go ahead and factor this thing, and we get x plus 5 and x minus 1. So those were the original denominators. And I'm putting a over x plus 5 and b over x minus 1. If you would put a over the x minus 1, b over the x plus 5, ultimately you'll get the same final answer I do in the end. You'll just have a swapped a and b values. But that's all that really changes. So the way we go about solving now is we multiply both of these fractions by the opposite denominator. And that creates equal denominators. So now it's all about making the numerators the same. So we'd be saying negative 3x minus 33 equals ax minus a when we distribute plus bx plus 5b. So the x coefficients have to match up to be negative 3. So that's going to be our first equation. We're going to say that negative 3 equals a plus b. And then our constants should match up to be the negative 33. That's our next equation. So we're saying negative 33 equals negative a plus 5b. For the most part, these will be set up in a way that you're going to probably use your elimination method, but you are obviously welcome to use substitution instead. Here it's clear elimination. I've got a and negative a, so they're just going to cancel when I add the equations together. Getting negative 36 equals 6b. Therefore, b is negative 6. Going back to the first equation, negative 3 equals a minus 6 gives us a to be a positive 3. So our final answer would have been 3 over x plus 5, and then plus a negative 6 over x minus 1. And that would have created the single fraction negative 3x minus 33 over x squared plus 4x minus 5 if we were to go through and actually get common denominator and combine them. But the idea is we're splitting it up. And this idea of splitting up is very useful for things that we're going to talk about next year in calculus. When we talk about integrating certain rational functions, the idea of partial fractions will be very helpful to split in to make it easier to do. So we're just going to do a couple examples with this. So obviously we could have a quadratic that factors a little bit more annoyingly because it's got a number in front of the x squared. That doesn't change the overall process. We find that factors as 3x plus 4 and x plus 5. We still multiply by the opposite denominator to go ahead and combine them so I can work with my numerators. So my 20x plus 23 would equal ax plus 5a, and then 3bx plus 4b. Again, my equations, I sum up based off the coefficients. The x coefficients are 20, and then a plus 3b. And then 23 for our constants, 5a plus 4b. Now, again, we can go through any method we want. I'm going to use a substitution this time around just to show you that you can use that option here. So the first equation, I can isolate a by saying it's 20 minus 3b. So I go ahead and fill that in for a here, 20 minus 3b. We get 23 equals 100 minus 15b, which is negative 77 when I subtract it over, and then negative 11b when I leave it here, so b is going to be a positive 7. And then we go ahead and plug it back in, so a would be 20 minus 3 times 7. 20 minus 21, a is a negative 1. So my final answer is negative 1 over 3x plus 4, and then 7 over x plus 5. And we would have gotten the exact same answers had I used an elimination or I done a different substitution. But obviously, if you're going to use substitution, stick with like A equals or B equals. It's a nice simple variable you can work with. Don't try and do it where I'm trying to isolate B, where I'm dividing everything by 3. And it will work. It's just going to create fractions that are unnecessarily entered into the question. All right, so that's your partial fraction decomposition. Now, this only really works, though, if you have what's called a proper rational function to begin with. A proper rational function is where the greatest exponent is in the denominator. So if the numerator is greater than the denominator or equal to it, you have to use long division to rewrite it. And I'm saying long division rather than synthetic division because typically you're dividing by quadratics or higher exponents than that, and synthetic division cannot work unless you're dividing by linear. So we are going to have to use polynomial long division to divide this. Once we get it into a proper format, we can then do our partial fractions with the resulting function. So here we're going to go ahead and divide the x squared plus 7x plus 12 into our x squared. I'm going to use my 0x for my placeholder, if you remember doing that, to keep everything lined up nicely. First term divided by first term, x squared over x squared is going to give us a 1. So we get x squared plus 7x plus 12, and we're subtracting. So 0 minus 7 is negative 7. Negative 10 minus 12 is negative 22. So our fraction becomes x squared minus 10. I'm sorry. The x squared minus 10 becomes, let's write it back over here actually, just simply 1 plus negative 7x minus 22 over the x squared plus 7x plus 12. And you can see the remainder portions now are proper rational function formats, which means now we can do the partial fraction based off that function right there, and we obviously just include the 1 in our final answer. So we have 1 plus a over x plus 4, and then b over x plus 12. Well, not plus 12, sorry, plus 3. Let's just fix that. And we're multiplying a by the x plus 3, the b by the x plus 4, and we're comparing those numerators to the negative 7x minus 22. So I'm kind of getting a little confusing with all the green, so I'm just going to switch up the colors here. So negative 7x minus 22 is going to be ax plus 3a, and then bx plus 4b. So negative 7 equals a plus b. Negative 22 is going to be 3a plus 4b. So we need to go, okay, we want to solve. So let's multiply the top equation by a negative 3, which makes it 21 equals negative 3a minus 3b. And then we can add the equations together to eliminate the variable a. We get negative 1 equals b. So once I get b is negative 1, I know negative 7 equals a minus 1. So a is a negative 6. So my final answer, I'll do down here in the bottom left here in red, is the 1 from the polynomial long division, and then plus the negative 6 over x plus 4, plus a negative 1 over x plus 3. If it's negative, also, you don't necessarily need to write as plus and negative. We could have just written both of these as minuses. So minus 6 over x plus 4, minus 1 over x plus 3. That's perfectly fine, and that's our final answer. So the key, again, comes from the polynomial long division step, and then solving the resulting linear equation system based on that information. All right, so let's go ahead and just do one more to give you enough practice with that. You definitely want to, if you haven't, try pausing it, try it on your own, and see if you're going to get the matching answer that I'm going to get right here. So we're setting up our long division, our 3x squared minus 11x minus 4, dividing into our negative 6x squared plus 23x plus 17, bringing in negative 2. So the negative 2 then multiplies the bottom to get negative 6x squared, positive 22x, and positive 8. When subtracting, obviously the 6x squared pieces cancel. 23 minus 22 is 1. 17 minus 8 is 9. So we get a negative 2 plus x plus 9 over our 3x squared minus 11x minus 4. So we set up our partial fractions. It's going to be a over our 3x plus 1 and then b over our x minus 4, the two factors of the 3x squared minus 11x minus 4. We're multiplying by the opposite denominator, so a times the x minus 4, and then b times the 3x plus 1. So we get x plus 9 is going to equal ax minus 4a, 3bx plus b. So our equation is going to be 1 equals a plus 3b, and then 9 equals negative 4a plus b. So what I'm going to do here is, let's see, let's multiply the top equation by a 4. So we get 4 equals 4a plus 12b. And I've been probably solving for a to eliminate that first or substitute with that first. You can do whatever you want. It's your system. It doesn't matter how you go about solving it. Like as I said in the beginning, we could have done Cramer's rule and inverse matrices with this. I wouldn't recommend it. I feel like it would be significantly longer than solving this elimination process right here where we get b equals 1, plug it back in, and get a equals negative 2. I think that's significantly quicker than trying to go through any sort of matrix setup here. But you're obviously more than welcome to do whatever you want when you're solving this thing. So our final answer is the negative 2. Our a was negative 2 as well, so it's minus 2 over 3x plus 1. And then plus, because b is positive, 1 over x minus 4. All right, and that's our partial fraction decomposition. Very useful, like I said a little earlier, for calculus next year. We get into the idea of integration. So if you're watching these videos from that class to review this, awesome. It's a good idea. If you're not in that class yet, I would recommend remembering what I said this and then referring back to this when you get that chance next year. All right, one more topic left in Unit 9, talking about solving systems of nonlinear equations. So quadratics and linears, and then quadratic and quadratics. So I'll see you next time for that.